Hi everyone, we are moving on today to related rates. So we've broken it up into a couple of different sections. So just so you guys know, related rates will most likely appear on the AP exam. It has appeared on every AP exam for the last, I don't even know how many years in a row. So the chances of it being on your AP exam are pretty high. So we have to make sure we understand these types of problems. So let's talk about what a related rates question is. So in the real world, a rate at which one variable changes can directly affect the rate at which something else changes. So let's look at what that really means. If the radius of a pumpkin gets larger, so let's say we have this pumpkin over here, whatever, I don't care that it's a blue pumpkin, no judging, and we've got this radius r, okay, and we're saying that it gets bigger. Well, then, if the volume, or I'm sorry, if the radius gets bigger, then clearly the volume is also going to increase. All right, so anytime we change the radius of the pumpkin, clearly the volume overall is going to change. And don't make fun of my pumpkin. I know it's blue and I know it's lopsided. Don't judge, all right? Yours don't look any better, I'm sure. Then, for this example, if a ladder slides down a wall and the base of the ladder is getting farther away from the wall. So let's actually go ahead and draw. Here's the wall, here's the floor, and we've got this ladder leaning up against the wall. So we're saying that the base of the ladder is getting farther away from the wall, so it's sliding this way. Well, then that means that the height of the ladder is also decreasing. If the base of the ladder is sliding to the right, then obviously the top of the ladder must be sliding down as well. So these examples right here are just going to have us looking at some equations. Before we do that though, I would like to talk about really quick, anytime we talk about these rates changing, we're talking about the variables changing with respect to time. And so what that means then is we have to differentiate with respect to time. All right, and anytime we differentiate with respect to time, it means we're going to use implicit differentiation. So that's actually why on the end of the optimization practice, you guys had some practice with implicit differentiation, because this is really going to be necessary for the related rates stuff that we're going to do. So, variables changing with respect to time, so we need to differentiate with respect to time. So we're going to review implicit really fast. So assume that the radius r of a sphere is differentiable function of t, and let v be the volume of the sphere. Find an equation that relates dv dt, which means the change in volume with respect to time, and dr dt, which means the change in the radius with respect to time. So the first thing we need to do then is write an equation for the volume of a sphere. So this is something that you guys should know, but the volume of a sphere is 4/3 pi r cubed. And we want to find the derivative with respect to time. So since this right here says dt, we know we're doing the derivative with respect to time. So if we use implicit differentiation, it's just dv dt equals, we drop the 3 and have 4 pi r squared, and then the derivative of r with respect to t would be dr dt. And that's it. That's our formula right there. Right now we're not doing anything more with it. For part B, assume the radius and the height of a cone are differentiable functions of t, and let v be the volume of the cone. Find an equation that relates dv dt, dr dt, and dh dt. So again, let's start by writing the volume of the cone. So volume of a cone is 1/3 pi r squared h. Well, now we're going to be taking the derivative, and we need all of these values to be in there. So we have to be careful here because we have r squared times h, which means we're going to need some product rule. So the first thing I'm going to actually do is write my constants together, make it pi over 3 r squared, and then h. So now if I take the derivative with respect to time, dv dt is going to equal, I'm going to start by leaving pi over 3 r squared alone and take the derivative of h, which is dh dt. So I leave my first function alone and multiply by the derivative of the second. And then plus, I'm going to leave the h alone now, and now I'm going to multiply by the derivative of pi over 3 r squared. So that would be 2 pi over 3r, and then times dr dt. So this one looks kind of nasty, I know, but that's how we would do that one if we need the product rule. So we're going to write down some steps for solving these related rates problems, and we're also going to make a big list of common formulas, but we're going to do that like as we use them. I'm not just going to write a bunch of formulas for you in a video. So we'll write them as we use them so that you guys can have a list of them, but they are formulas that you're going to need to know for the AP exam. They're not going to be given to you. So step 1 for the related rates problem is that we're going to draw a detailed and labeled picture. Now something that's really, really important, so I don't know if you guys have a highlighter or if you've got some colors or what, but put some stars next to this. This is super important. You do not put numbers in your picture unless they are constant. And we'll talk really about what that means when we look at some of the examples, but that's going to be a super, super important concept as we move forward with these problems. Now, these next couple of steps can be done in a different order, so I'm actually going to change the order that's on here. So if you'll do me a favor and cross off 2, 3, and 4. So once I draw my picture, I actually go to here and I write an equation that relates the variables. And your hint here is that you want to think about geometry formulas. So in both of the last examples that we did, we used some volume formulas. There's other ones that we're going to use too, but always think about geometry. All right, then I go to here and I take the derivative of the equation. And I'm going to add here with respect to time. All right, we're always going to take the derivative with respect to time t. Then I go up here and I list the variables and their derivatives. And fill in the values that I know. And the last thing that I do then is I solve. And you want to make sure, because these are real world problems, we want to make sure that our answer has the correct units in it. Okay, like I said, these common formulas we're going to list together as we use them, so we'll be coming back to this page a lot. But the first one that I do want you to write down, this first video deals with related rates problems that use Pythagorean theorem. So I do want you to first write the Pythagorean theorem for me, so that we can make sure we all remember Pythagorean theorem. It's a squared plus b squared equals c squared, where c is the hypotenuse of a right triangle. Okay, so let's do some examples together. We're going to do the first two, and then we're going to do the third one in class together before you guys do some practice on your own. Okay, so like I said, these all deal with Pythagorean theorem. An airplane is flying towards a radar station at a constant height of 6 meters above the ground. If the distance s between the airplane and the radar station is decreasing at a rate of 400 kilometers per hour when s is 10 kilometers, what is the horizontal speed of the plane? So let's remind ourselves, the first step we're going to do is draw a detailed and labeled picture. So I can't draw an airplane. If you can, cool, more power to you. But I'm just going to go ahead and draw a dot, and I'm going to say, hey, that's my airplane. Because I can't draw a plane. I'm sorry, you're stuck with me as your teacher, and I'm not an artist. So there's my airplane, and it's flying at this constant height, and it's flying towards a radar station. So it's flying this direction, and I'm going to say that my radar station is down here. All right, so we have this triangle then that looks like this. The airplane is flying up here, and the radar station is down here on the ground. So we said that we need this detailed and labeled picture, and we only put numbers in if the numbers are going to be constant. That's actually why I underlined this constant height of 6 kilometers, because I can put that in my picture. So my height above the ground is 6 kilometers, and that never changes. Then let's see what else I know. The distance S between the airplane and the radar station. So here's my airplane, here's the radar station, that's S, and I'm going to call this horizontal distance X. All right, so now I have my picture. That's my step 1. Every single time is to draw that picture. Then step 2 we said was to write an equation that relates them. And I already even told you guys that we're going to use Pythagorean theorem. So we're going to write x squared plus 6 squared is equal to s squared. That's our step 2. Step 3 then is to take the derivative of this, and we have to remember we're taking the derivative with respect to time. So I get 2x dx dt. 6 squared is really just 36, which is a constant, so the derivative of that is 0. So this is going to equal 2s ds dt. Okay, so this was my step 2. I wrote my equation. Step 3 was to take the derivative. So now we're moving on to step 4, which was to list the variables and their derivatives and fill in the values that we know. Well, in order to use this formula, I can see that I need to know what x is. I need to know what dx dt is. And then I have got s and ds dt. So when we take a look here, let's see what we do know. The distance s between the airplane and the radar station is decreasing at a rate of 400 kilometers per hour. First of all, I want to point out the fact that it says it is decreasing. And what's decreasing is the distance between the airplane and the radar station, which means since it's a rate, that's a derivative. And so that means then that ds dt is negative 400 kilometers per hour. And it's negative because the distance is decreasing. So make sure you include that negative there. So then, what else do we know? S is 10, so we can fill that in. And it asks, what is the horizontal speed of the plane? Well, that means we're looking for dx dt. So somehow we still need to be able to find x. So we know that when s is 10, we can just use our Pythagorean theorem to solve for x. So we have x squared plus 36 equals 10 squared. So x squared plus 36 is equal to 100. X squared is 64, so we get that x is equal to 8. Now, some students prefer to draw a picture for when we look at this specific example, so this would be a 10, a 6, and that's our x. If you do that and you can look at it and use your Pythagorean triples and know that that's 8, that's cool too. But either way, we get that x is equal to 8. So step 5 then is to actually solve for what we're looking for. So if we go back to this, we know 2x is 8, dx dt is what we're looking for. And then we've got 2 times, I'm sorry, I ran out of space here, I write too big. S is 10, and then ds dt is negative 400. So if we simplify, let me go like this so I can write here. So if we simplify, we get 16 dx dt is equal to negative 8,000. And then when we divide that over, we get that dx dt is equal to negative 500. And then we need some units here. Since this is a speed, it's a rate, we're talking about kilometers per hour. And so that is our final answer. Sorry, I kind of ran out of room there. But I'm going to go ahead and write my final answer over here as well, because I'm going to write it a teeny little bit differently. So the horizontal distance, the rate of change of the horizontal distance, no, the horizontal speed of the plane, sorry. Gosh, I can't speak. When s is equal to 10 is equal to negative 500 kilometers per hour. So this is just another way to write it so that we know specifically what it is we're looking at. So I just want you guys to be able to see that. Okay, the second example we're going to look at is a ladder problem. These are very, very common, so I do want to make sure you guys know how to do these. So we've got this 6-meter ladder leaning against a wall. So let's start by first drawing the wall and drawing the floor. All right, and we've got this ladder leaning up against the wall. All right, it says if the bottom is pulled away from the wall at a rate of 1/2 meters per second, how fast is the ladder top sliding when it reaches 3 meters up the wall? Which means the base is sliding to the right. Okay, well, again, the only numbers that we want to put in our picture are ones that are constant. And the length of the ladder, guys, that's not going to change. All right, it is always going to be a 6-meter ladder. So we're going to put a 6 there. And I'm going to call my horizontal distance x and my vertical distance y. So there's my detailed and labeled picture. There's my step 1. Step 2 then is to write the equation. So that would be using Pythagorean theorem, x squared plus y squared equals 6 squared. And step 3 is to take the derivative with respect to time. So 2x dx dt plus 2y dy dt equals 36, and the derivative of that then is 0. So that's my step 3. Step 4 is to write the variables and derivatives that I need. So I know that I need x, and I need dx dt. I need y and dy dt. So let's see what I know. The bottom is pulled away from the wall at a rate of 1/2 meters per second. Well, this distance is getting bigger, so that's a positive 1/2, and that's my x that's changing, so that's a 1/2. How fast is the top of the ladder sliding when it reaches 3 meters up the wall? Which means that my y value is 3. And it's asking how fast the top is moving. That's my dy dt. Which means somehow I can find the x value. So again, some students will draw the picture again, some students will just go right to Pythagorean theorem. But we know that when y equals 3, we'll have x squared plus 3 squared equals 6 squared. So x squared plus 9 equals 36. X squared equals 27. So we get that x is equal to the square root of 27. So I'm going to go ahead and put that here for my value of x. And now step 5 then is to go ahead and solve. So 2 times the square root of 27 times 1/2 plus 2 times 3 times dy dt equals 0. So I'm going to go ahead and start simplifying. 2 times 1/2 cancels, so I really have the square root of 27 plus 6 dy dt equals 0. 6 dy dt is equal to the negative square root of 27. And so I get dy dt is equal to the negative square root of 27 over 6. And I can actually simplify this. The square root of 27 simplifies to 3 root 3 over 6. And so my final answer then is negative root 3 over 2. And I'm going to again go over to the side here and write my final answer. So I know that dy dt when y equals 3 is equal to negative square root of 3 over 2, and then I need some units here, meters per second. So this is my final answer. I know this is kind of a lot. I know this video was a little long. I'm sorry, but this is a really, really important concept for you guys to understand. So hopefully you're good. We'll do example 3 together in class, and then you guys will get tons of practice. See you later.